Alright, in this video we are going to dive into distillation columns for homework 3 part A of separations. And so I'm going to start off by drawing some schematics of the rectifying, stripping, and feed sections of the column with a total condenser. And then I will make some material balances around envelopes of those different sections, derive some equations for the rectifying and stripping operating lines and the Q line for the feed, which we will use this information in future parts, and I'm going to get into that right now. Alright, so what I did was I took a photo of a kind of diagram of a distillation column from my notebook, and as you can see, lots of stuff written here, but we're going to break it down further. And so up here above this feed line, we have the rectifying stage, and below the feed line we have the stripping stage. As you can see, the vapor is rising, as vapor does, and the liquid is falling down as it condenses, and they are transferring mass and temperature, things like that, as they move through this distillation column. Up here we have our condenser, and down here is, I labeled this the reboiler. And what happens is when vapor comes up and gets into this condenser, we're assuming a total condenser. So all of the vapor, every bit of it gets condensed into a liquid, and it collects in this reflux drum. A certain percentage of it flows out into the product that we call the distillate, and a portion of it is refluxed back into the column, and it'll continue to interact with the other components that are flowing through the system still. And the liquid that falls down to the bottom, this reboiler will vaporize the components, and what comes out as a liquid is the bottoms. So ideally what gets turned back into a vapor would be your more volatile component. If some of it ends up in this area for some reason, the more volatile component is going to come out up here, and the less volatile component will end up down here. You will have some of each in the other spots as well, but that just depends on how your process is set up. And this bottoms, it's called bottoms, it's the other product. So we have the top product that is containing mostly, if you have a 2-component system, it'll contain mostly the more volatile component, and the bottoms would contain the less volatile component. However, if you have, more like a multi-component system with more than 2 components, then your things are going to look a little bit different. But for now, we are looking at a 2-component system, which simplifies a lot. And so what we want to do is kind of divide these up into 3 sections: the rectifying section, the stripping section, and the feed section. And then we will derive those equations that I was talking about. So first I'm going to start with the rectifying section, that top section. And so since that is that top section, I'm just going to draw it like this. We have a feed coming in, and Then we have our column, Let me make that a little thinner. So we have our column, and I'm going to be referring to everything above the feed, so not anything below. And what you have in a distillation column typically is these trays. These trays allow for optimum heat and mass transfer, so the liquid can flow through, the liquid overflows down and the little gas bubbles rise, typically through holes, or it just depends on how your trays are set up. But it looks something like that. I'm just going to get rid of that for now to simplify this diagram if I can. And so we're talking about the rectifying section up here. I'm going to change this feed so I can kind of like color code a little bit. We have the feed in there. This tray here will be our N, and this tray will be our N+1. So from this top tray we have a vapor leaving, that is Vn, and from this tray we have Vn+1 because it is below, and that's just how we write that. And then we have a liquid coming down from stage N and a liquid coming down from stage N+1. And then we can't forget our reboiler, or sorry, not our reboiler, our condenser at the top. This is our distillate, and then our reflux. Obviously this is not the best diagram, but you can kind of see how it relates to that one up there. Also, if you wanted to, you could label this as N and this as N-1. It's the same thing. Subtracting just means you're going up the column. So in the rectifying section, what this does is the liquid basically removes volatiles from the vapor components that it's interacting with, enriching the vapor. So from the previous tray we have Vn+1 right here, and Yn+1. Y is just our vapor concentration of the more volatile component. And we set that equal to the liquid times the liquid composition plus the distillate times the distillate composition. Again, that's the composition of the more volatile component. And we also know in general that Vn+1 has to be equal to the liquid plus the distillate flow. We have, if this was N+1 here, it is a combination of what's coming down plus the distillate that left already. Hopefully I'm explaining that correctly, like in an understandable way. But yeah, so with some like just algebraic manipulation, we can get our, basically I'm replacing this Vn+1 with L plus D in this equation. And now we solve for Yn+1, so we're solving for the stage below's vapor composition, essentially. That would be L over L plus D, liquid plus distillate, times the liquid composition of the stage above, plus D divided by L plus D, times the liquid composition of the distillate, And then something else I want to define is the reflux ratio. As we talked about, the reflux is right here. In my previous diagram, it was right here. So that is what you reflux back into the column, basically to continue driving the reaction the way you want it to go. If you took out absolutely everything from the top into distillate, it just would not run very well. Your purity wouldn't be very good, etc. So, reflux ratio. We define that as being the ratio of the liquid to the distillate. So as I was saying here, the vapor coming up was equal to the liquid plus the distillate flows, but this ratio, this reflux ratio is L over D. So it's the ratio of what's being returned as a liquid to what exits as distillate. And so we can actually sort of simplify this by using the reflux ratio in the equation itself, because the reflux ratio is, very commonly understood. It's understood what it means when you see an R in kind of a distillation column problem. So you have yn plus 1, that's the vapor composition at the stage below, is equal to R over R plus 1 times xn plus 1 divided by R plus 1 times xd. And this is our rectifying operating line. So we've done the schematic and the equation for the operating line. And so what we want to do next is I'm going to do the stripping next and then the feed later on. So now for the stripping section, basically opposite of what I said for the rectifying section, this lower part of the column removes the volatile component from the liquid and transfers it into the vapor as that rises up. And so I'm just going to draw this a little bit more simply. We have the feed going in, and we know that above is the rectifying section, which we already did, so I'm just gonna draw it like that. I don't know why that's so crooked, just ignore that. And then down here, right here, is the stripping section. Again, we have trays, and again, it'd be n and n plus 1. Technically speaking, we would have it be, we would have n here, n plus 1 here, and like I was saying, as you go up, you're subtracting. So it'd probably be more, I guess, technically correct to write it like that here, but also when you say n plus 1 versus n, you know if you're talking about the stage above or the stage below. So it doesn't really matter too much. And we write things pretty similar here. The vapor is the same, it's Vn, V sub n, but we put a bar above just to make it obvious that this is in the stripping section. So we do the same thing here, V bar n plus 1. And then our liquid coming down, we do the same thing, we add a little bar above. And obviously we have our reboiler here. Essentially you get liquid coming down, vapor returning, and then some of that is exits as the bottoms. I'll just label that as B to be consistent with what I did above. And now we're basically doing a really similar thing. We know that L, as we said up here, L plus D is equal to Vn plus 1. This is very similar. We're saying that the liquid is equal to the vapor plus the bottoms. So this liquid here is equal to the vapor exiting the reboiler plus the bottoms leaving the reboiler. That's just a material balance. And we also know that the liquid times the liquid composition of stage N is equal to V bar times, and as I go on, I'm probably not going to say the bar every time. Just know that you should write it when you're talking about the stripping section, but I'm not going to say that like every single time. This is Vyn plus 1, so the vapor composition of the more volatile component in the stage below. So we have that, and then we also need to add the bottoms. And when we add the bottoms, similar to what we did with the distillate, we multiply by the liquid composition of the bottoms. And again, we're going to replace this L with this V plus B in the equation. So we get V plus B times Xn is equal to V Yn plus 1 plus B XB. And then we isolate our Yn plus 1. So we would have V bar plus B times Xn minus B XB divided by V. And similar to the reflux ratio, we're going to define a boil up ratio. And I'm, instead of using B, because that's what the variable we're using for bottoms, and that would get confusing, I'm going to say V sub B. And so that is the boil up ratio, and that is equal to the vapor leaving divided by, or the vapor re-entering the column divided by the bottoms leaving the column. And similar to what we did for the rectifying section, we're going to put that boil up ratio in our operating line. So we have Yn plus 1 is equal to this VB plus 1 over VB times, this up here should be an Xn. So that's times Xn. We still have our minus, and this becomes 1 over VB times XB, and that is our stripping operating line. Oops. Operating line. So we did the rectifying, we did the stripping, and now we need to do the feed section. As you can see down here, we don't have a feed line or feed operating line like we did for the rectifying and stripping. However, we do have something called the Q line, which is basically a very similar thing, but it describes the feed. So I'm not going to draw another schematic of the feed section, but obviously you would have feed going in, you have our rectifying above, and our stripping below, and then you have vapor coming up and liquid going down. And I would just follow the numbering scheme I have here. And don't worry about exactly where your feed is entering at when you're like just drawing this out. That's something you kind of determine later on when you are numbering the stages and things like that. But it's just entering somewhere kind of between those rectifying and stripping sections. And so for our feed section, we want to find the Q line. So first I want to talk about what Q is. So in long terms, the Q line kind of represents the physical state of the feed mixture. It mainly tells us the quality, how much liquid is in there. And then I quickly looked over my notes really quick to make sure I had these numbers right. But essentially, if your Q value is greater than 1, you have a subcooled liquid. If it's equal to 1, you have a saturated liquid. If it's between 0 and 1, you have a liquid and vapor mixture. If it's equal to 0, you have a saturated vapor, and less than 0, superheated vapor. So that's kind of what Q tells us about the feed. And from the rectifying section, we said Vn plus 1 times Yn plus 1 is equal to Lxn plus dxd. And the stripping section, we had, remember we're using the bar here, Lxn is equal to Vyn plus 1 plus bxb. And when we combine them, since the feed is technically like between the two, when we combine them we get this V minus V bar times Yn plus 1 is equal to L minus L bar times Xn plus Bxb plus dxd. And it should be noted this right here is F times ZF. I just use this Z rather than X or Y because it's just defining the composition, not of the liquid or the vapor specifically, but just the general composition of the more volatile component. And then this F would just be the flow of the feed. We also define this V minus V bar as being 1 minus Q times the feed. 1 minus Q times F times, I'll just write this out really quick. In a more simplified way again, because I defined this FZF and I forgot to put that in. What you notice is that we can cancel out all these F's, just divide by F. And then we're left with 1 minus Q times Yn plus 1 is equal to negative Q Xn plus ZF. And again, solving for Yn plus 1, we would get Q divided by Q minus 1 times Xn minus ZF, just because of those plus and minuses, and divided by Q minus 1. I guess like you could also, to keep it more consistent, I'm going to write that as 1 over Q minus 1 times ZF, but obviously that's the same thing. And so I made this green. I'm trying to color code and stay consistent this time. This is our Q line. Just to run through that kind of one more time, we talked about just in general what a distillation column kind of looks like with my drawing here that doesn't translate super great onto digital, but it's okay, because I drew these little schematics. And so we did our rectifying section here, and we got this wonderful equation. And in a future video, you'll see why we need this equation, or like what it kind of has a few purposes, but obviously if someone gave you the distillate composition, the liquid composition of stage N, and the reflux ratio, then you can solve for the vapor composition of the stage below. And similarly, if you had this but not one of these, you could do that. Same thing with the stripping section. We had our stripping section here, our equation there, and again, you can use that to solve for things. You can also use it for plotting, which, like I said, we will get into, I believe, in I think the next video. And lastly, we did our Q line. This represents the kind of how much of the feed is liquid or vapor, essentially. And yeah, hopefully that covers all the bases for that. All right, it's already the end of the video, but basically we went through those different sections of a distillation column, and in the next part, we're going to talk more about the boil-up ratio and reflux ratio, a few other things with the components, and then we are going to generate what is called a McCabe-Thiele diagram. And once I kind of do that diagram, it'll make more sense as to visualizing these equations. So thank you for watching.